Imagine for a second, right, that you are trying to understand the fundamental character of a massive, rapidly changing country.
Right.
And I mean, really understand how the land itself functions. Usually, you pull up a standard map, you look at the political borders, the state lines, the county jurisdictions. But what if you stripped all of those imaginary lines away?
Yeah, just totally remove them.
Exactly. What if instead you looked strictly at, like, the DNA of the Earth beneath those borders?
I mean, it forces a complete shift in perspective. You quickly realize that the way we politically divide a landscape,
Mhm.
it almost never matches the way nature actually operates.
Right.
Like, ecosystems do not stop at a state line just because a politician drew a boundary there, you know?
Yeah, nature doesn't care about our signs. So today we're doing a deep dive into a 2026 study by Inesh and a team of researchers, and they did exactly this to Nigeria.
Hmm.
Taking this rapidly urbanizing nation, we're talking over 229 million people, and feeding its raw environmental DNA into a machine learning algorithm.
It's incredible.
It really is. So our goal today is to explore how these researchers took just an overwhelming amount of open access data and distilled it down into an interactive open source map, one that captures the unique, sometimes pristine, and often really fragile typologies of Nigeria's physical landscape.
And, the stakes for understanding how that land is structured, how it's changing, are incredibly high right now.
Oh, absolutely.
Nigeria is experiencing some of the fastest population growth and urbanization on the planet. I mean, if you want to manage that growth sustainably, you need to know exactly what you're building on.
Right, you can't just guess.
Exactly. And that requires a very specific approach known as a landscape character assessment, or LCA.
So let's break that down for everyone because a landscape is, well, it's far more than just what you see growing on the ground, right?
Yeah, exactly.
How did these researchers actually define a landscape's character?
So historically, in places where this kind of assessment has been used for decades, like across Europe, for instance, it often included these highly subjective elements.
What do you mean by subjective?
Well, planners would factor in things like scenic beauty or the historical feelings associated with a region.
Oh, interesting.
Yeah, but this study took a parametric approach instead.
Meaning entirely objective, data-driven.
Precisely. A parametric approach relies strictly on measurable, quantifiable variables. They defined landscape character as the intersection of physiographic elements, so the natural earth itself, and cultural elements, which is how humans are covering or using that land.
Okay, got it.
To build this profile, they gathered 4 massive countrywide data sets at a 1-kilometer resolution.
Which is incredibly detailed for an entire country. And if we're building a landscape from scratch, right, the absolute base layer has to be the geology.
Right, the literal foundation.
Yeah. They classified the parent material of the Earth into 5 broad groups. You have these massive sedimentary basins, metamorphic rocks, and then these like ancient, undifferentiated basement complexes that just form the very foundation of the terrain.
And then on top of that foundation, you need the elevation. They divided this into 5 classes, starting from the coastal lowlands, sitting right at sea level, and stretching all the way up to the high-altitude peaks of the Jos Plateau.
And then you have to apply the climate. So they broke Nigeria down into 6 distinct climatic zones.
Spanning a huge range, right?
Oh, totally. From the highly humid tropical rainforests all the way down in the south up to the really arid Sahelan conditions in the far north.
Right. And finally, the 4th ingredient is the land cover. Now, this data was sourced from the European Space Agency and broken down into 9 cultural types.
Okay, so what falls under that?
This is your prop land, dense tree cover, built-up urban areas, mangroves, bare land, things like that.
I always think of this like baking a cake.
Okay, I like that going.
If you're trying to understand the cake, the land cover, so the trees, the cities, the crops, that is really just the frosting. It's what you see on top.
Right, the superficial layer.
Exactly. But to really understand what kind of cake you're eating, you need to know the geology, which is your flour. You need the elevation, which is like the baking pan giving it shape.
Yeah.
And then you need the climate, which is your oven temperature.
That analogy perfectly illustrates why you can't just map the trees and say you understand the ecosystem,
Yeah.
Because a dense forest growing on a low-altitude sedimentary basin in a highly humid climate, it's going to behave very differently than a dense forest growing on, say, a high-altitude basement rock formation.
Right. The whole system changes.
Exactly. The water retention is different. The soil vulnerability is different. The heat dynamics are completely different.
But wait, hold on. If we mix all these highly distinct data points across an entire country, so we've got 6 climate zones, 5 geologic groups, 5 elevation classes, and 9 land cover types, doesn't that just create a totally chaotic, unreadable map?
Well, yeah, that was the massive hurdle they had to overcome. If you simply multiply the theoretical possibilities of just the natural Earth, just the climate, geology, and elevation, you get 96 different physiographic combinations.
Wow.
And that is before you even add the 9 types of land cover frosting on top. If a human geographer tried to sort through millions of these data points to find meaningful patterns, I mean, it would be a mess of bias and noise.
Which is why they didn't rely on humans to draw the lines.
Nope.
They brought in a machine learning algorithm.
Exactly. They utilized an unsupervised machine learning approach called k-means clustering.
Wait, unsupervised, meaning without a guide.
Yeah, unsupervised means the algorithm is not given an answer key. It isn't trained by humans to find specific things like forests or cities.
Oh, fascinating.
Instead, it looks at the millions of 1-kilometer pixels of data across the country, and it groups them together purely based on their mathematical similarities across those 4 variables we talked about.
Okay, so think of it like being handed an airplane hangar filled with, like, billions of loose Lego bricks.
Yes.
You have absolutely no idea what a car or a castle is. You are just told to start sorting them based strictly on their shape, their color, and their size.
That's a great way to put it. The algorithm is doing exactly that, but with pixels of environmental data.
But how does it know when a group is actually a group? Like, isn't there a risk of the algorithm just drawing arbitrary boxes around completely random data points? How do we know these landscape categories aren't just, a math trick?
The researchers worried about that exact issue. You can't just tell an algorithm to find clusters without giving it a way to measure its own success.
Right.
So they built in these statistical fail-safes called gap statistics and silhouette coefficients.
Gap and silhouette. Okay, how do those actually grade the machine's homework?
So the silhouette coefficient measures the internal consistency, or basically the tightness of a cluster. It looks at a single data point and asks, how similar is this pixel to the other pixels in its assigned group compared to the pixels in the next closest group?
Ah, okay, so making sure it actually belongs where it was put.
Exactly. And then the gap statistic measures how non-random the grouping is compared to a completely uniform, flat distribution of data.
So they are literally trying to find the mathematical sweet spot where the boundaries drawn represent a sudden significant shift in the real-world environment.
Yes, exactly. Because if you force the machine to make, say, 100 base clusters, the differences between them become so microscopic that they're completely meaningless for a city planner.
Right, it'd be too noisy.
So by running these statistics, they found the real spatial coherence. The math revealed that when looking strictly at the natural Earth, so just the climate, geology, and elevation, there were exactly 25 optimal physiographic clusters naturally occurring in Nigeria.
Okay, so we have 25 base cake recipes. But we still have to add the frosting, the land cover.
Yeah, and when they integrated those 9 types of land cover data into those 25 base clusters, the machine generated 131 distinct landscape character typologies, or LCTs for short.
Wait, 131 typologies? That still sounds like a nightmare for a regional planner to actually use.
It does sound like a lot, doesn't it?
Yeah, because satellite data is incredibly noisy. You might have like a single pixel of cropland detected in the middle of a massive concrete city.
And nature is messy, which is exactly why they implemented a spatial generalization process.
Oh, what's that?
Well, to make the map practical, they applied a filter that absorbed tiny sliver patches, anything under 5 square kilometers, into the larger surrounding areas.
Oh, I see. Because you don't zone a major metropolitan area based on a single rogue tree pixel.
Exactly. The filter smoothed out the static noise while still preserving the true diversity of the landscape.
Okay, that makes sense. And I guess the burning question here is the accuracy, right? A machine made these 131 groups completely without human supervision. How well did the math actually reflect the ground truth?
Very well, actually. They generated over 3,200 random validation points across the country to test the model against reality.
Ooh.
The resulting map had an overall accuracy rate of 74.41%.
Wow.
Yeah, and in the world of broad-scale landscape mapping, anything over 70% is considered highly robust for operational use. The algorithm's mathematical groupings genuinely captured the environmental reality on the ground.
That's incredible. So the researchers successfully built this highly accurate machine learning model of Nigeria's landscape. But, a 74% accuracy rate on a complex math model doesn't mean anything if a local conservationist in Abuja can't read the code.
Exactly.
Like, what good is a revolutionary map if it just sits locked away in some static academic PDF?
Overcoming that communication barrier was actually a core goal of the study, because a map is only as good as its accessibility, right?
Yeah, totally.
So they didn't just publish their findings and walk away. They created a dynamic, interactive dashboard using a platform called Tableau Public.
And the dashboard is incredible because it completely democratizes the data. Like, you can go online right now, pull up this map of Nigeria, and just hover your mouse over any specific spot.
Hmm.
And when you do, it pulls up a distinct code for that exact typology. Every single one of those 131 landscapes has its own unique identifier.
Right. Let's take an urban example to see how it works. You hover over a built-up area, and you might see the code C2G4E1L50.
Which, I have to say, sounds incredibly technical at first glance.
It does. It sounds like a password. But the dashboard instantly translates that code into plain English for the user.
Oh, really?
Yeah, it tells you that you are looking at a landscape characterized by a tropical, wet, and dry climate. That's the C2.
Okay.
It's situated on a sedimentary rock formation, so that's G4. It's at a very low altitude, between 0 and 100 meters E1, and it's predominantly covered by built-up urban areas, which is the L50.
That is so cool. It literally translates the raw, overlapping DNA of the Earth into something a human can actually read and understand instantly.
Right.
But they took it a step further than just building a neat visualization tool, didn't they?
They did. They've rigorously followed FAIR principles, which stands for findable, accessible, interoperable, and reproducible.
Nice.
They uploaded all the raw data sets, the Python code used for the machine learning, and the computational protocols onto open repositories like GitHub and the Open Science Framework.
You really have to realize how incredibly rare this level of transparency is for broad-scale national mapping.
Oh, absolutely.
Particularly in developing nations. Usually this kind of data is locked behind proprietary software, or a government commissions a map once and then it immediately becomes outdated like 5 years later.
It just sits on a shelf.
Right. But because this code is entirely open, it serves as a living framework. When the European Space Agency releases new land cover satellite data next year, literally anyone can run this exact same algorithm and update the map for free.
It creates a sustainable ecosystem of knowledge. But, as we know, a tool is only useful if the people on the ground actually want to use it.
I was just going to ask about that. Did they actually test this dashboard with stakeholders? Like, did real urban planners and foresters find it useful, or was it just a shiny tech toy built by researchers for other researchers?
Oh, they tested it thoroughly. They shared the dashboard with 11 Nigerian stakeholders across a bunch of disciplines, like urban planning, forestry, climatology, and agriculture.
Wow, quite a mix.
Yeah. And they asked them to rate its validity against the reality they actually experience out in the field.
And how did it do?
The stakeholders rated its validity and usefulness at an average of over 4 out of 5 stars.
That's amazing.
They confirmed it provides this incredible, reliable baseline. Though, a few noted they would still need narrow, field-specific inputs for highly localized microscopic projects. But as a broad tool, it was a massive hit.
Okay, so we have this powerful dashboard, the stakeholders validate it, and the machine learning accurately maps the terrain. How do these 131 interactive landscape typologies actually change how a nation manages its environment on a day-to-day basis?
Well, the most profound realization from this tool brings us right back to the beginning of our deep dive. Nature completely ignores political borders.
Right, the imaginary lines.
Exactly. And this data visualizes that reality perfectly. For example, the tool reveals that the built-up urban sprawl of massive cities like Lagos has expanded far beyond its administrative state and local government lines.
Because the built-up landscape typology doesn't just magically stop because a sign on the highway says you are leaving Lagos state.
Nope.
And that means managing that urban environment, managing the traffic, the water drainage, the pollution. It requires cross-state cooperation because multiple jurisdictions are literally sharing the exact same landscape DNA.
It forces planners to look at the ecological zone, not the political zone. And it's not just about managing urban sprawl either. It is crucial for protecting pristine environments.
Oh, how so?
Because the algorithm grouped identical landscapes together regardless of where they were geographically, it highlighted highly unique, contiguous ecological zones that might have totally gone unnoticed in a piecemeal, state-by-state survey.
Right. There is a fantastic example of this in this study, actually. Typology code C2G4E1L10.
Yes, that one translates to a pristine, dense tree cover landscape sitting on a low-altitude sedimentary basin in a wet and dry climate.
And what the map revealed is that this single, fragile, continuous ecosystem spans across 12 different southern states in Nigeria.
Thorough states.
12 states sharing one unified ecosystem. Just think about what that implies for conservation. If you want to protect that ecosystem or maintain green corridors so wildlife can migrate, you cannot have one state aggressively clear-cutting it while a neighboring state tries to pass conservation laws.
It just wouldn't work.
Exactly. The tool identifies exactly where ecological connectivity is needed, allowing the federal government to coordinate protection across all 12 states simultaneously.
And this approach has massive implications for national policy. The sources actually provided two concrete examples of how this data redefines resource management.
Oh, let's hear them.
The first involves the ACRESOL project.
Ah, the Agroclimatic Resilience in Semi-Arid Landscapes project.
That's the one.
It's a major government initiative specifically targeting land degradation and desertification. And currently, the boundaries of that project are aimed at 20 states, primarily in northern Nigeria.
But when you apply the machine learning landscape assessment and you ask the dashboard to highlight all the vulnerable typologies, so the specific bare lands and fragile shrublands in those arid climates, the map shows those typologies do not stop in the north.
Really? Where do they go?
The ecological degradation is actually bleeding southward into states like Edo, Manambra, and Enugu.
Wow. Which suggests that a multi-million-dollar environmental intervention project might need to drastically reevaluate its borders. They need to base their funding and resource allocation on where the vulnerable landscape actually exists, not just on the political jurisdictions traditionally associated with the North.
Exactly. And the second policy example addresses surface urban heat islands, or SUI. The researchers linked mean land surface temperature data to these specific 131 landscape typologies.
Well, we know that concrete absorbs and holds heat much more than a forest does. But how does mapping the typologies help manage that?
So they've found that in the southern parts of the country, the built-up urban typologies have significantly higher land surface temperatures than the natural landscapes immediately adjacent to them.
Okay.
When you remove specific vegetation typologies and replace them with concrete, you break the microclimate cooling effect. The algorithm's temperature data spiked specifically within those L50 built-up zones.
Now, urban planners have an interactive map showing exactly which specific typologies are baking. It provides a precise, targeted tool to manage urban heat dynamics. You can look at the map and know exactly where you need to mandate green roofs, where you need to plant shade trees, or where you need to alter building codes to cool a specific neighborhood down.
It shifts landscape planning from being reactive to being incredibly proactive. It takes the guesswork out of environmental management for a country of 229 million people.
That's huge.
Yeah, planners are no longer guessing where the desert is moving or where the city is overheating. The algorithm just shows them the exact boundaries of the problem.
Let's bring this all together. We started with raw, chaotic satellite data covering climate, rock formations, and elevation. We watched an unsupervised machine learning algorithm sift through 96 possible physical combinations to find the 25 true base layers of Nigeria's Earth. We layered on the land cover frosting to reveal 131 unique landscape typologies.
A lot of frosting.
Right, and we saw how that mathematical complexity was transformed into an interactive, open-source dashboard that empowers local stakeholders to protect fragile ecosystems and manage exploding urban growth.
It is truly a masterclass in making environmental data both mathematically rigorous and practically useful for the people who actually need it. To plan for the future, we have to understand the foundational character of the land we are standing on.
This study really proved that the true character of a landscape rarely matches the political borders we draw on maps.
Yeah, nature has its own map.
So I want to leave you with this final thought to mull over today. Think about your own city, your own town, your own neighborhood.
Okay.
If an impartial algorithm were to strip away your county lines, your city limits, your neighborhood zoning laws, and it only looked at the deep DNA of the Earth, the climate, and the development beneath your feet, what larger hidden landscape would you suddenly discover you are a part of?
Oh, that's a great question.
Right. Who are you truly connected to ecologically that a standard map has never shown you?
It completely reframes how you view your own backyard.
It really does. Thanks for joining us on this deep dive. We'll catch you next time.